So welcome to the third lecture on Laplace transform. And क्या कर रहे थे हम? पिछला कोई याद है? पढ़ने का शौक निकल तो नहीं गया अचानक क्या बना? पिछले 2-3 लेक्चर किस बारे में थे?
सर frequency domain.
Yes. Going from discrete time to
Frequency.
continuous time, right? और then discrete time में जो time domain है उसका we saw its equivalent in continuous time, right? And also the frequency domain in discrete time we saw counterpart of that in continuous time. इधर ये n वगैरह में होता था, इधर ये time domain t में n was discrete where t is continuous. इधर क्या हुआ था? Z transform था, इधर क्या आ गया उसकी जगह? Laplace transform, right? And then the lecture after that, after transitioning to this, we discussed properties of the Laplace transform, right? We practiced some Laplace transform for delta t, e minus at ut, right? Ut like that. And we also briefly reviewed properties of the Laplace transform. Linearity, right? Linear hai. It converts convolution into product, those kind of things, right? So we quickly reviewed that because we have already done that in Z transform. Then we did one more thing after that in the last lecture, which was to model CT LTI systems, right? So for DT LTI systems, we had modeled them as difference equations, right? क्या मतलब इससे? Let's say we were saying that yn is 4xn plus 2xn minus 1 plus 3yn minus 1. Let's say in discrete time, this is how we were writing. What was this? This was a model of a discrete time LTI system. It is a linear combination of past inputs and outputs, right? This we call difference equation. And we saw that to solve this kind of difference equation, you had to do it iteratively, yes, with some initial conditions if they are not zero. That was a pain. So one side benefit of the Z transform turned out to be it converted the difference equation into simple algebraic equations. And we saw that in great detail 3 or 4 lectures ago. Now, in the last lecture, we saw a counterpart of this for continuous time. What was that? We said, okay, how do you model a continuous time LTI system? We said you can model it as a differential equation in inputs and outputs. So instead of the difference equation, I'm basically drawing the chart that summarizes what really happened. Yeah, it models the inputs and outputs as differential equations. What do we mean by that? Well, in there we could have that dy t by or let's say just for simplicity we write it dy by dt second derivative plus 4 dy by dt equals, let's say, some input function 5x, for example, right? So then what we had now was differential equation, right? In input and output, both of them can be function of time here. So instead of a difference equation, you had differential equation. And who helped us there? The Laplace transform. So the Z transform did this magic. Yeah, here who did that magic? The Laplace transform. Again converted into algebraic equations, and then solving these is just standard way, usually by partial fraction expansions and things like that. Yeah. So far in the last 2 or 3 lectures, this is what we have done. We've gone from what we had covered in great detail in like 14 lectures to continuous time, all of that translated. Yeah. So today we will just close this thing, wrap up this thing, just a very short summary left to complete this part. Yeah. Just a few things that we need to elaborate on. Another thing that we did have here in discrete time, LTI, not just the model of the system. We also looked at how can you tell if an LTI system is stable, causal, all that, right, based on its impulse response. So for DT-LTI system, by now you should know that if the impulse response sequence, the total sum of this sequence, absolute sum of this sequence is finite, we say that the DT LTI system is stable. For continuous time, we covered something similar. What was it? It was the integral, right? So area under this continuous function, impulse response. If this is finite, then we say the continuous time LTI system is not much different, right? Since this is continuous, you need continuous sum, which is an integral. This is discrete, so you need a discrete sum, which is just a summation as you know it. Yes. So, और इसके पीछे reason we have already covered where we got this from. But when we were translating to continuous, we didn't go back to that, right? But you can look at the old lectures again and the notes and find out where did that come from. But for now, we were just translating it to continuous time systems. Now, what we haven't looked at is something very useful in the frequency domain, which is stability in the frequency domain. So, what is the Laplace transform of the impulse response? Yeah. For the discrete time case, we said the Z transform of Hn was, remember, Hz, and we called it the transfer function, right? Exactly same thing happens here. The Laplace transform of the impulse response of a continuous time LTI system is the transfer function. And now what's the variable here instead of Z? Laplace का कौन सा है? S. Because Laplace is like Zn becomes E
power
st.
S.
This S, right? S है ना? So
otherwise
otherwise no change. Yeah, this was the Laplace Z transform of the impulse response. We call it the transfer function. This is also called the transfer function for the continuous time case. Now, from the transfer function, can I tell if a system is stable or not, bibostable or not? Okay, that's one question we will answer today. The second thing we will do is just look at one example of this thing happening. We will have an LTI system modeled as a differential equation. We will convert it into algebraic equation and solve it. By solving, we mean find the formula for the output in terms of the input. अभी तो ये सारा mix हुआ हुआ है ना derivatives के अंदर. How do you get yt out of this? Yeah? So that we will look at. So first let's start here. In the time domain, we know that a LTI system is bibostable if its impulse response satisfies this. Total area under the absolute of the impulse response is finite. Okay. How does that translate to this thing? Okay. So that's a very interesting thing. Have you heard of zeros and poles? किस कोर्स में सुना? सर्किट एनालिसिस में क्या होते हैं zeros and poles? अब आप सोच रहे हैं कि हम कहते नहीं सुना सुना हुआ है तो ये सुनने से आगे भी आप हाँ सुनने से आगे का स्टेप कब आता है? When do you guys go to the next step? Usually या बस तारुफ तक ही बात चल रही है. Okay, it's okay. So
सर्किट्स में कोई उनकी वो इक्वेशंस नीचे डिनोमिनेटर में
हाँ.
जीरो से ऊपर पहुंचते
Oh, ऐसे ही है ना? हाँ, exactly. It's good. It's a good start. Now remember when we wrote the system as in the Laplace domain, remember हमें ये फॉर्म आ रही थी बार बार,
यस सर
right? And I said that this thing, well, you could look at it if initial conditions are 0. This thing can be the HS. Okay, but let's look at this first. Here, now often the rational transfer function can be written like P over Q form. Yeah, that means आपने जब partial fraction expansion भी की थी, but even without that, what we could have, let's say we write the transfer function in the rational form, and then we factorize the numerator and the denominator. Okay, so let's say we get in the numerator s minus b1, s minus b2, and so on, s minus bn, let's say, and in the denominator we get s minus a1, s minus a2, and so on till s minus bn. Okay, वो जो आप कह रहे हैं ना, ये है वो, right? What are the zeros now? Zeros are the roots of the numerator, right? Assuming that we have cancelled out, अगर ये कोई b1, b2 और a1 की वैल्यू सेम है तो ये cancel out हो चुके हैं, ठीक है? I'm assuming I have the reduced form, minimized form. फिर उसमें देखते हैं आप, what are the roots of the numerator? वो क्या वैल्यूज हैं जो न्यूमरेटर को जीरो बनाती हैं? तो वो है s equals b1 because b1 minus b1 will be 0. Similarly b2 factorized form में जो रूट्स सामने आ जाती है ना, so zeros are what? Roots of numerator. Yeah, why is that? Because they make the whole thing 0, right? What about poles? As you said, अब रूट्स डिनोमिनेटर की भी हैं, राइट? क्या रूट है इसकी? कोई एनी रूट यू कैन टेल. a1 is a root, right? If this was s minus 10, then 10 would be one of the roots of the denominator. So they are still roots, but of what? Of denominator. ठीक, इनको हम zeros कहते हैं, इनको poles कहते हैं, ठीक है? And poles tend to take you towards infinity, right? Zeros tend to take you towards 0. Okay, yeah. So in different contexts, yes, we look at these Bode plots and these things. We look at the zeros and poles to say identify how a process will be affected. Here what we are interested in is to see how they affect the stability of a system. Okay, that's the key thing that we want to look at. Now let's see. You saw that we were able to write for z transform at least, and the same will hold here. We were able to write, you know, इसकी आप partial fraction expansion कर सकते हैं, ठीक है? In that case you are often able to write the this guy. Let's say I'm just giving you one example. Let's say I have written some or done some partial fraction expansion of some LTI systems transfer function, और वो ये बनी है. Let's say ये तो generic है ना, लेकिन let's say दो roots. There were only how many poles as, so you will have to basically see. But let's see. Let's come to if you have done the partial fraction expansion of this system. From here, can we tell if the LTI system for which this is a transfer function is bibostable or not? Okay. Now, firstly, the corresponding HT, इसका जो भी HT बनना है, उसका हमें पता है. उस पे क्या condition है for stability? Absolute area should be finite. We know that. z इसका जो लाप्लास इनवर्स ट्रांसफॉर्म बनना है उसमें हमें ऑलरेडी पता है, राइट? the impulse response absolute area should be finite, but we don't know this thing. Okay, let's try to see what happens. अगर मैं इसका इनवर्स लाप्लास लूँ, okay, आपको शायद अभी तो probably don't remember that formula, but it was like e minus at ut had a Laplace transform 1 over s plus a. Okay, you don't have to memorize that thing, you'll have the table, but I'm just recalling, helping you recall here. ये था, ठीक? It works both ways. So now look at this. If I wanted to take the inverse Laplace of this, what would ht be?
E power minus 3t.
E minus 3t ut, yes, plus
E power 4 minus 4t.
twice e minus 4t ut. Okay, very good. Remember, the question we're trying to answer is, can I tell from here if the system is bistable or not, without doing this? But first we have to do it once or twice to see if there is a pattern. By the इससे क्या पता, इसको मिला के if you read, what do you say? Is this system bistable or not? सोच के ut only says that this is not existing before t0, right? So it starts at t0. What is this function? Imagine करिए function sinusoid है, growing exponent है, decaying exponent है, क्या है? decaying ना, क्योंकि ut before t negative तो allowed ही नहीं है, तो positive आएगी तो -3 times 1 -3 times 1.5, all of these negative. So if you imagine this function, what is this term? Decaying, right? And exponentially decaying. What about this term? Exponentially decaying. That means since these are both exponentially decaying, you can check that the area under this will be finite. Okay? Now it's like a convergent series. Convergent series में क्या होता है, आपका infinite terms तो add कर रहे हैं, लेकिन they are approaching a limit.
Yes, sir.
Right? Same is here. You are adding some area. It's not ये रुकता नहीं है वो, क्योंकि asymptotically it approaches. But each time that becomes exponentially smaller than the previous, so we can see that it's approaching some value. Yeah. So what's happening here? The whole thing has an absolute area which is less than infinity. Okay. Right. अब ये तो हमें टाइम में बता. Can you link this thing to the poles? इससे सिर्फ दाल में इसके poles क्या हैं? Poles are the here they are the roots of the denominator, which make this whole thing infinite basically, right? S को अगर a1 रख देंगे तो a1 minus a1 0 हो जाएगा, this thing का infinite. Yeah. Here क्या क्या है poles?
3 and 4.
-3 and -4, right? Do you see them somewhere over here?
Yes, sir.
Where are they?
E power minus 4.
हाँ, powered में है ना ये?
Power S.
Here they are, right? So this thing has poles -3 and -4. Okay, that's good. And we know that these poles, they show up as it is here. Okay, now let's imagine that this thing was 1 over s minus 3.
Positive.
Okay, then what would ht have been? E 3t ut. What is its pole? 3. 3 shows up here. Is this इसका area बताइए, exponentially growing है या decaying है? Growing है. So the area under this guy, absolute of this guy, is infinite. What happened? Just by changing the sign of the pole, you can tell from the sign of the pole if this system is stable or not. You'd from now on, if you have written your transfer function in a reduced form and you find its poles. What is roots of the denominator? If you find its poles, and the poles happen to have negative sign. Okay, let's say -3, -4. 3 or 4 would make it unstable. Why is that? Again, it's not abrupt nahi hai. Now from here on you will use in many courses that if the poles are in the left half plane, the signal system is stable. Okay, this is not something they made up. Idhar se nikli hai. It's here. You can see it happening, right? So if the poles now, agar what is S, by the way? S याद है? Laplace transform का जो variable है. Any complex number, right? So that means in general S lies in the complex plane, right? This is the plane where X lies. This is the real component. This is the imaginary component. Okay. What is the requirement on the poles for this thing to be stable? क्या requirement थी? Sign उनका negative होना चाहिए, right? So where can they lie? S की कोई वैल्यू लें, यहाँ पे ले लें, चले, ठीक है? अब बताएं, is the real part positive or negative? Positive. What about the imaginary part?
Still positive.
Still positive, yeah. Either what happens here?
Positive or negative.
So the real part is
Negative.
negative, yeah. So essentially that is what we are mainly interested in here. The left half plane. Okay, that will lead to this thing being negative. Now why aren't we concerned about the imaginary part becoming negative? What is this? Let's say you have E S T. Okay, now let's say S is -3 plus 4j. Real part is negative, okay, other part is positive. What does it become? It's -3, right, plus 4j t. Okay, can I write it like E -3t times E 4jt? Can I write that?
Yes, sir.
Right, okay. Now this, you know, what is it? Exponentially decaying. What is this? Complex? No, it's not up. Euler identity लगाएं. E j theta क्या होता है? It's a complex number, right? This का real part is cosine, imaginary part is sine. It's a sinusoid. और अगर आप इसको polar में देखेंगे तो it's a circle, right? Which is neither growing nor decaying. But then who is adding growth or decay? This guy. So the sign of the imaginary part doesn't matter. Okay, that's why we are not restricting ourselves to here. The real part and the imaginary part both have to be negative. All we need for the system to be stable is to be in the left half plane. That means the pole should have a real part which is negative. Okay, so again, what are we saying? Poles, अगर यहाँ पे poles हैं, your system is stable. Why is that? Because we know now, whenever you have a pole here, it will look something like this. क्या होगा उसका? जो real part है वो negative होगा, imaginary part या positive होगा या negative होगा. But decompose करके when you look at it, it turns out that the imaginary part plays no role in decay or growth. वो एक fixed level पे रहता है. Right? So negative, the imaginary part doesn't matter. You can be here or here. However, as soon as you change the sign of the real part, the system either is growing, decaying. So if you were here, for example, then what are you looking at? Maybe you are looking at E3t minus 4j. Sorry, E3 minus 4j times t. Now look at this E3t times e minus 4jt. This is just a sinusoid thing. This is exponentially growing. Your system has become unstable. Okay, clear what?
Yes, sir.
So from here on we drop all of this story, but you should know it. You can't say right? So revise that. But from here on we drop the whole story and we say what? The transfer function in its most reduced form, take its poles. What are the poles? Zeros of the roots of the denominator. Take its poles. If the poles are in the left half imaginary plane, your system is stable. If they are not in the left half plane, your system is unstable. Okay, इसमें कोई है सवाल quick सा? No. So just do a quick revision of that. What happens, by the way, let's say this was in this system we had s plus 3 and s minus 4. Now one pole is in the left half plane, the other pole is in the
Negative.
right half plane, right? अब ये system stable है या नहीं? Unstable है,
Yes, sir.
right? Why is that? You need only one term to grow infinitely for the whole thing to grow infinitely, yeah? So although this is decaying, this guy is growing exponentially. If you take the absolute area under that like we do for HT, the whole thing will be going to infinity, yeah? So as soon as even one pole shows up in the right half plane, you have unstable system. Okay, now for discrete time, this is for continuous time systems, right? Discrete time में क्या होता है? Instead of hs you have hz, right? And in hz you have, if you remember, we were writing things in the form of z over z minus some gamma, yeah, writing the poles and zeros like that. So let's see quickly what happens in the discrete time case. Any guesses? Discrete time में कहाँ होना चाहिए poles को? For continuous time, poles have to be in the left half plane. Okay, let's see. जो आपको help करेगी इसमें चीज वो ये formula है. If you remember, we found the z transform of gamma and un to be z over z minus gamma.
Yes, sir.
Okay, ये हमने find किया था. And then we were also rewriting in partial fraction expansion this thing like that. Okay, so for simplicity, without going into too much detail, let's say this is hz, okay, and this is ht, okay, sorry, hn, this is discrete time, yeah. Now from here right now you cannot tell what you need for the system to be stable, but from hn you know what is that? Summation absolute of hn should be less than infinity. So if you compare this here, what are we saying? Are we saying summation gamma n un just means this starts at 0, right? So we can remove that if we want, but we're saying this thing should be less than infinity, right? What is that? So summation gamma n should be less than infinity. If this was minus infinity to infinity, you can remove 0 un to just write it 0 to infinity, yeah? What does this remind you of? We have looked at this before. Geometric series. Right? When is a geometric series convergent? When?
R is less than.
Yes, this R, absolute of this R or gamma is less than 1. Right? यही था ना?
Yes, sir.
So now look at it here. What is the root of this? What is the pole of this equation? Z equals? No, Z equals gamma or R. Yeah? This system has pole Z equals gamma. If that gamma's absolute happens to be less than 1, it will lead to an impulse response which is bistable. So now we have a shortcut. What is that? Should be less than 1. Up in complex plane, what does gamma less than 1 mean? I have done this before, so probably you can guess now. In the complex plane, there is a gamma here. Okay, what does this mean? Absolute of gamma less than 1.
First coordinate.
Absolute of a complex number, what does it represent? Modulus, right? What does modulus represent?
Positive.
No, that's for real, yeah. In so if you are looking at real number line, 4 has absolute modulus 4 and minus 4 has modulus 4, right? That's on the real line. What is this really saying? It's telling you how far is this number from the origin. ये 4 units दूर है और ये भी 4 units दूर है. Distance क्या है? Doesn't matter किस direction क्या है, right? So that is what it's doing. So in complex plane, that is the same thing. It tells you how far is a complex number from the origin. Where is the origin?
0.
Here, right? So when a number is far, just far as 1, that means it lies on a circle of radius 1, right? अब कोई भी number, any complex number in here satisfies this thing. What is this? Again, remember this absolute आप लोग जो कहते हैं ना, that operator is not just absolute or modulus. It's the distance of the number from the origin. अगर वो real line है तो origin यही है, or so you can only be on this line. If it's complex plane, then you are looking at a circle. Because origin is here, then you could be a distance of 1. Within that distance of 1 here, अगर ये 3 dimensional होता तो फिर क्या होता? Sphere. Okay, so actually it goes up high to n dimensions. Okay, you can imagine an n dimensional sphere where all the numbers satisfy this, that they are within this unit distance from the origin. Right, so in conclusion, what did we find for stability? Let me summarize that very quickly. This is topic of bibostability in frequency domain. Okay, so in frequency domain we then say, okay, in continuous time Hs corresponds to Ht, and since we know that 1 over s plus a corresponds to e minus at ut, we say from Hs stable if poles in left half plane. Okay, for discrete time we have Hz corresponding to Hn, and there we have this formulation z over z minus gamma corresponding to gamma n un, and from here we can see that Hz tells us about stability. From Hz you can tell if the system is stable if poles inside unit circle. Distance of 1, yeah, inside unit circle. Now the whole idea of left half plane and inside unit circle comes from here. देखें, left half plane में होगा तो ये negative रहेगा और decay करेगा. So that's what it makes. यहाँ क्या होगा? Within unit circle means कि gamma absolute will be less than 1, which is requirement for any geometric series to be convergent. That's all. So इसमें कोई magical नहीं है. But from here on we just skip this whole story and we say when you have written a system in the frequency domain and written in the most reduced form, so there are no repetitions in numerator denominator, then if you see the poles in left half plane, system is stable if it's continuous. If the system is discrete, look for the poles. If they are inside the unit circle, system is stable. As soon as the poles go outside the unit circle, they become unstable. Okay, so as I said, we will do one quick example of the other thing that we wanted to see was differential equation becoming a algebraic equation with the help of a Laplace transform. Let's say we have a CT-LTI system, continuous time LTI system, and let's say it's written like, as I said, it will be written as a differential equation. So I'm going a bit fast because it's just numerical thing. Okay, so what is this system? We're saying this is a CT-LTI system that has input xt and the output is yt. Okay, now it's easier said than done here. Yeah, it's very easy to say, okay, the input is xt, the output is yt. If I tell you, okay, now the input xt equals 10, what's the output? You look at it and you say, oh, okay. Apparently you have the relation, but what's happening? The output is stuck inside derivatives. Even the input is stuck inside derivatives, right? So to get yt now, you have to solve this differential equation. So let's use the method that we have from Laplace transform. Okay, so we have covered, when we did the discrete time systems, we have covered what we call zero input response and zero state response. Okay, so if you remember, I'll just make a quick table of responses. A system can have zero state response, which means that its initial conditions are 0 and you give some input. Okay, that's zero state response. Then there is zero input response, which is the system has input 0 and some initial conditions. It's driven by the initial conditions. Lastly, the total response of a system. You remember ye kya tha? We did this in detail for discrete time. Okay, so what was the total response? If we call this ZSR and we call this ZIR, then total response is simply, for LTI systems, it's the sum of the zero state response and zero input response. Okay, so this gives us a trick to solve this thing or find the output by dividing the problem into two sections. Okay, the first one is what? Set the initial conditions to 0, give it the input and get the zero state response. The second is assume that the input is 0 and put in the initial conditions and get the zero input response and sum them up to get your total response. So let's do that very quickly for this example, and then we are done for today. So let's see, I will let's say that the input, of course I have to tell you the input to get the output. Yeah, so let's say I say that the input given to this system was this thing, e minus 4t ut. Okay, that's the input given to this system. Now can you find its let's say we start with zero state response here. Can you find its zero state response? So what does that mean? Zero state response means that you will assume initial conditions are 0 to get the zero state response. Okay, now let's take the Laplace transform. What's the Laplace transform of the derivative, second derivative? S square ys. Remember?
Yes, sir.
We discussed properties of the Laplace transform. What else is there? If the initial conditions are not 0, you actually have minus s y dot 0, if I remember correctly, and minus y0. Okay, or the dot is here, I don't remember. First derivative basically. Yeah, but what are these initial conditions? Okay, are we bothered about them right now? No. When we are doing zero state response, we don't care about them because we say, okay, we're going to assume they are 0. So that means I don't have to write this whole thing all the time. All I need is the first term, this thing, yeah, s square ys. What about the second one? What does it become? 5
Y.
ys, but there is a derivative. What's the derivative? Second derivative is s square, third derivative is s cube, so on. And then there is an initial condition. Again it's 0, so forget it. Plus 6 ys. What about this guy?
X.
So
X is zero.
xs but s. Why the s? Derivative, right? And then there will be minus x0, small x0, but initial conditions are 0, so we drop that. Plus xs. Agreed? Now let's solve this. I will quickly rewrite the final thing so you can verify that. And this is what it should look like. Agreed or not? S, take a y as common, you are left with s square plus 5s plus 6. That is here. Right pe jab gaya. Well, how about this? Take xs common, you are left with s plus 1. See, because of the Laplace, I am dealing with the differential equation as a simple algebraic equation. Just do multiply, divide, left, right, everything, yeah? But now, what is xs? What's this? What's the Laplace transform of this? We have seen that 1 over
S plus 44.
s plus 4, right? So let's put that here also, because where is it? Yeah, this is xs, right? So let's put that here, 1 over s plus 4. Okay, now we do partial fraction expansion of this. I will skip that. We have done that for z transform. You can see in your book also. But basically the partial fraction expansion will lead us to s plus 2 plus 2 over s plus 3 minus 3 by 2 s plus 4. Okay, now can I do inverse Laplace of this? क्या बनेगा इस टर्म का? minus half times e raised to minus
-4.
2, ये 2 है,
Minus 2.
2t ut, yes, plus 2 times e raised to
minus
3t ut, right? Minus
3 by 2.
3 by 2
E की power
e minus
40
40 ut. So you have found the output, but with initial conditions 0. Okay, so we call it y0 state response. हो गया? Zero state response. अच्छा. Now to get the zero input response, what do? Now you go for the second part. I will erase this. आपने जब differential equation solve की होंगी ना, तो you must have done complementary solution and particular solution. We were doing something like this there, okay, already. So किया होता है, maybe with some other name, right? So now we go for zero input response. What does that mean? It means that xt equals 0. Okay, that's zero input response. And then we ask them, okay, what are the initial conditions? If they are also 0, then what you already found in zero state response is your full answer. because there is nothing to do here. But if the initial conditions are not 0, let's say they are not 0, let's make it a bit interesting. So we say that y0 is 2 and y dot 0 is 1. Okay, these are the initial conditions and there is no input. Okay. So now let's do the Laplace transform of this. अब क्या बनेगा इसका Laplace transform? S square, right? Ys minus what? Minus sy0 minus y dot 0. Okay. Now we cannot ignore these because there are some initial. पिछले part में we assumed there was, but now the simplification we made was here. Okay. So ये एक term की जगह ये तीन आई अब. Okay, which is the general case by the way. We only skip them because when we assume initial conditions are 0, that is often the case. What about the second one? 5ys, sys minus y0. Okay, अभी वो डालेंगे values हम यहाँ पे. What about the last one? 6ys. What about the right hand side? Quickly. 0. Because we are solving for this case. Right? ये नहीं कर रहे हम लोग. 0 input response. So 0 here. Now let's put the values. y0 is 2. Y dot 0 is 1. Y0 is 2. If I put all of those here, I am left with s square ys plus 5sys plus 6ys equals 2s plus 11. Okay, ये कहाँ से आया 2s plus 11? 2 times s, right side पे गया तो positive हो गया. Where is the 11 coming from? 11 कहाँ से आया? 5sys, that's here, right? 6ys is here.
तो उसमें से
ऐसे ही आ गया. एक सेकंड, just a moment. s square ys minus sy0, that is 2s, right? And then there is oh sorry.
Then minus 1.
Yeah, actually this 5 is multiplying the whole thing. Sorry, ये miss कर दिया, right? 5 times the whole thing है ना, तो वो पूरा का पूरा अंदर जाना था. Yeah. So 5 times 2 was 10 plus 1, 11. Yeah. Okay. So mystery solved. Now क्या होगा इससे? Again, you can rewrite this as ys equals 2s plus 11 divided by s square plus 5s plus 6. ऐसे लिख सकते हैं ना?
Yes, sir.
I just took ys common, send everything else to the right. अभी इसके साथ क्या करेंगे आप? Our favorite partial fraction expansion. I won't do it here, but if you do that, the partial fraction expansion, you will end up with this thing. Ys is 7 by s plus 2 minus 5 by s plus 3. Partial fraction expansion का तरीका ये ना, you factorize this thing, right? Then you write it as a over one factor plus b over other factor. Then you use cover up rule to find a and b. You found them to be 7 and 5. That's it. कोई उसमें थोड़ा सा time लगता है, लेकिन otherwise it's not, conceptually it's not hard. Right. Now what is the Laplace transform? 7e minus 2t ut minus 5
E minus 3t
ut. And what was what was this found? What was the assumption? Zero input. So let's name it zero input response, so we don't confuse. इससे पिछला हमने क्या find किया था? Zero state response, right? What was that? That was minus
1 by 2.
half e minus 2t plus 2e minus 3t minus 3 by 2 e minus 4t ut. Yeah? Exactly. So now you are ready to give the total response of the system, which is simply okay. Just sum them up. ये और ये terms add हो जाएंगी. Whatever अगर इनमें is minus 2t, then they will sum up to make whatever they want. Similarly here, 2 minus 5 हो जाएगा. This is new, so it will stay as it is. This now is your solution. Okay, and something similar to this you do all the time in differential equations. Maybe someday I can just show you again what the differential equation thing is. Next time I will go through this thing again briefly. Yeah, but don't get scared by the large number of equations, right? Key concept थोड़ा idea हुआ है नहीं? इस lecture में since we have done this part already for discrete systems, so it's not. जो नई चीज थी इस lecture में ना, वो क्या थी? Stability from the frequency domain. So far we had not looked at stability in frequency domain. Today we just did that, and we found that you can tell if an LTI system is stable from the frequency domain also. How do you do that? If it is continuous time, look at its transfer functions, poles. If the poles are in the left half plane, it's stable. Okay. If it is discrete time, again look at its poles of the transfer function, and if they happen to be inside unit circle, it's stable, right? And we, behind this statement, what is the logic, what is the mathematics, what is the concept behind these two statements, we did that today. So आप review करेंगे, you will get to know, right? Okay, so what questions do you have? Can we go? Can you repeat the lecture? No? Okay, so right, thank you so much.